The device you're watching this on right now, it has billions, literally billions of tiny switches inside it, and every single one is smaller than a virus. They are the absolute bedrock of our modern world. But here's the thing, they're hitting a wall, a quantum wall. Today, we're going to pull back the curtain on the tiny engine that runs everything and find out why its future is a lot more complicated than you think.
Just for a second, really look at your phone or your computer. Inside that case, there's a microscopic universe. It's like a city of light and electricity, and it's all being conducted by one single component, the transistor. It's the invisible engine that, no joke, powers our entire civilization. And when I say a universe, I am not exaggerating one bit. A single chip in a modern smartphone can have billions, that's billions with a B, of these transistors. Every one of them is incredibly tiny, all working together in perfect, lightning-fast harmony. Okay, but what are all these billions of tiny things, actually doing? How does something so small create the amazing digital world we live in every day? Well, to figure that out, we have to go inside. So let's take a journey. We're going on a microscopic expedition to see how this fundamental building block of literally all modern electronics really works. At its core, a transistor is just a switch. But it's an unbelievably small, fast, and reliable switch that has zero moving parts. It can flip on and off billions of times every single second. And that simple action, on, off, repeated billions of times, is what allows your computer to compute. Now, this little marvel didn't just appear out of nowhere. You have to go all the way back to 1947 at Bell Labs. 3 incredible scientists, Bardeen, Bratton, and Shockley, created the very first working transistor. And it was a total game changer. It replaced the huge, hot, and frankly unreliable vacuum tubes of the day, and basically kicked off the entire digital age. So how does this magic switch actually work? Well, it's got 3 key parts. The easiest way to think about it is like a dam. You've got the source, which is like the big reservoir of electricity. You've got the drain, which is where all that electricity wants to flow. And then you have the gate. And the gate, well, that's the floodgate that controls everything. And here's where the magic happens. Think of the gate like a faucet handle. When you apply just a tiny bit of voltage to that gate, it creates an electric field that opens up a channel right through the semiconductor material. And boom, electricity can now rush from the source to the drain. The switch is on. Then you just remove that voltage from the gate, the channel closes up, the flow stops, and the switch is off. That's it. It's that simple and at the same time, that profound. So for decades, the goal was really simple. Just make the transistors smaller so you can fit more of them on a chip. That's what gave us Moore's Law and the mind-blowing technological progress we've seen. But as we shrink down to the scale of actual atoms, we run into a really, really big problem. The demand for more power, more speed, more efficiency, it's just relentless. For decades, the mantra in the industry was simple. Make it smaller, faster, and smarter. Engineers were in this constant race to shrink these switches, packing more and more and more of them into the exact same space to build exponentially more powerful chips. But you get to a certain point, a truly microscopic point, where the very laws of physics that run our universe start to push back. We've officially entered the quantum realm. And yeah, the old rules just don't apply anymore. And this right here is the shocking truth. When the gate that's supposed to stop the flow is only a few atoms thick, the electrons start to cheat. They do this thing called quantum tunneling. They literally just pass right through the closed barrier, like it's not even there. This causes leakage, it wastes energy, and it creates a ton of heat. The perfect switch starts to fail. So what do you do when the fundamental laws of physics are standing in your way? Well, if you're a semiconductor engineer, you get incredibly creative. You can't break the laws of physics, obviously, but you can find really clever ways to work around them. This is what they came up with. This is the engineers' modern-day toolkit for building at the nanoscale. They started using new materials to help electrons move faster. They pioneered fabrication techniques that can literally etch circuits atom by atom. And maybe most brilliant of all, they completely reimagined the transistor's basic design. The solution was to go 3D. See, the old transistors were flat, or planar, with the gate just sitting on top. But as it got smaller, it lost control. The breakthrough was a design called the FinFET. Instead of being flat, the channel rises up like a little fin, and the gate actually wraps around it on 3 sides. This gives the gate a much tighter grip on the flow, effectively slamming the door shut and stopping those leaky quantum electrons. So here's the key takeaway. By solving these insane microscopic quantum-level problems, we unlock massive, real-world capabilities. So let's zoom back out for a second and see what all this incredible engineering has actually built for us. It's almost impossible to overstate the impact. I mean, every single piece of advanced technology that defines our modern world rests on this foundation. It's really no exaggeration to call the transistor one of the most important inventions in all of human history. Think about it. The artificial intelligence that is changing everything, the whole network of smart devices in our homes, the advanced medical equipment that saves lives, even the computers that take us to other planets, all of it, every last bit, is powered by trillions of these tiny perfect switches. You know, the story of the transistor is far from over. Right now, engineers are already designing the next generation with new architectures and new materials. So it really leaves us with a fascinating question. If this is what we've already built with this little tiny switch, what on earth comes next? What kind of future is it going to unlock?